discussed mainly metamers and tautomers, that is metamerism and tautomerism. I hope you understood that. If you have any doubt, you can let me know. I'll see what can be done in that case. If you didn't understand that properly, you can let me know. And if you have any doubts, we'll take it later. For the time being, I'm starting with the next topic, that is geometrical isomerism. So in geometrical isomerism, we have already seen, right, that the structure won't have any difference. There will be some difference in the orientation, right? And we have seen different types of geometrical isomers as well, but not in detail. So when this geometrical isomerism comes into picture, so when there is a restriction in bond rotation. So when there is a restriction in bond rotation, then you will see this happening, right? And why there will be a restriction in bond rotation? So there will be a restriction in bond rotation. One, if there is a case of multiple bond. Second, if there is a presence of ring in the structure. So in both the cases, there will be a restriction in bond rotation. So that means once you have what this actually means. Suppose there is a multiple bond like this. There is a carbon here and a carbon here. And then carbon has two more valencies to satisfy. Now this can be anything. It can be chlorine, maybe hydrogen and chlorine. So because this bond rotation about this double bond, this rotation is not allowed. This rotation is not possible. Why? Because there are two bonds. One is sigma and one is pi. Sigma is axial bond, or sigma is formed due to axial overlapping, so it can rotate. But pi bond is lateral overlapping. So suppose there is a p pi bond, so it will be lateral overlapping of these orbitals, and obviously it won't be easy for them to rotate, right? So only it is due to the pi bond, one case. Second case, if there is a compound like this, right? A compound having a ring. So now here on each vertices of this rectangle which you are seeing, there will be two valencies, right? So again here, suppose in these there is H and H, here there is H and Cl, here hydrogen and hydrogen, and here H and Cl. Right? So once it is fixed, once this structure is it comes into existence, then it cannot interchange by rotation of any bond to some other configuration. So what I'm saying is configuration or orientation. So the orientation cannot interchange to another orientation. For example, in the first case, a possibility, another configuration which will be possible can be this Cl, Cl, H, and H. But these two cannot interchange, right? That is what I'm saying, I'm trying to say. It cannot interchange from one form to another directly. Just by rotation of bond, it is not possible. In the same molecule, without any proper chemical reaction or without cleavage of an existing bond and formation of new bonds, it won't be possible for one orientation to change into another orientation. So that means these two orientations are two different orientations. Although the structure is same, but orientation is different. Such entities, for example, in first case, the two entities which you are seeing above, these two entities are called geometrical isomers, right? And this phenomena is called geometrical isomerism. Okay, so what should be the conditions for geometrical isomerism? Let's see that. So the first condition for geometrical isomerism is what? There must be restriction in rotation, which we have already seen. And restricted atoms should have different substitute. If you go back to the previous example, right? The example here, where we have chlorine, chlorine, hydrogen, and hydrogen. What if all four are hydrogen, or what if all four are chlorine? Then even if you see the second orientation, both the orientations, or in both the molecules, there won't be any difference. So it's not just the restriction, there should also be asymmetry, or there should be different substituents in those restricted sites, right? So the first condition is what? First condition is that there has to be restriction in rotation, first of all, and that comes due to multiple bond ordering, we already know. And the atoms which are restricted to rotate, right? The restricted atoms, those restricted atoms should have different substitutes. Let's try to understand this with a generic example. Let's say you have A and B, and connected by a double bond, and then you have two substituents at A. Let's say that is small a and small b. Then even B has two valencies, suppose. Then here there can be AB, there can be AB connected like this, or there can be some other substituents as well, right? So what you see here is that this A and B, they are the restricted atoms. So they are the restricted atoms. Then there are two other substituents at A, and they are different, and two substituents at B, and they should also be different, right? So two substituents at A, and both are different. And even there are two substituents at B, and both of them are also different. What will happen if one of them is same? Or let's say A double bond B, there is A, and here there can be anything. Let's say there is A and B, right? So as per this example we have, so what we see here is these two are not different. It should have been different. But if it is not different, then what happens, right? What will happen is, if you do the other possibility of what, or before moving to this part, let's understand what is the point of this, or what is that orientation. We are saying that orientation is different, right? But what is that? How can we say that the arrangement or the orientation is different? So you can see here, chlorine and chlorine in the first molecule, they are on the opposite side. Hydrogen and hydrogen, they are on the opposite side. But in the second molecule, that is here, chlorine and chlorine are on the same side, and hydrogen atom are also on the same side. So here, opposite side, here, same side. We'll see what the nomenclature of this we will see later. But for the time being, as you can see, the atoms are on the opposite side in the first structure, and they are on the same side of the double bond in the second structure. So that is the difference. Now, if you see here in this case, if the restricted atom, let's say A, has both the atoms or substituents attached to it same, then what will happen? How will you have a different orientation? You try doing that. A double bond B. You try to change the orientation, right? This is A, this is A. There won't be any change here. On the second side, on the side of B, even if you do a change, it will be this. And what you observe here, these two are the same configuration or same orientation. There is no difference between these two molecules. Are you able to find any difference between this A and B?
Yeah. So, okay.
They are same, right?
Yeah.
Okay.
So I have a question.
Yeah, go ahead.
So they're geometrical isomers, even if the position of A and B are different? The small a, small b.
Yes, yes. You want to say in the, see, this is, let me show it once again. In this case, that is on the left side of the green line, geometrical isomerism is possible. Here I am saying that geometrical isomerism is not possible. Now, what is your doubt? Can you repeat your
Is it
doubt?
because, okay, why isn't it not possible, geometrical isomer for the A part?
Okay, see, what will be the other orientation for this? This, right? B.
Yeah,
And is there any difference between these two? See, how do we
no,
say difference? In the first case, you can see chlorine, chlorine on same side or chlorine, chlorine on opposite side. Hydrogen, hydrogen on same side or hydrogen, hydrogen on opposite side, right? Now here, what will you say? In the first structure, that is in structure A, right? In this structure, A and B are on the opposite side. Here also A and B are on the opposite side. Then A and A are on the same, are on the opposite side. Here as well, A and A are on the opposite side. Is it clear?
right,
So A,
yeah,
B are on opposite side. This A and this A are on opposite side. So in both the configuration, both the orientations are actually same.
okay,
Is it clear? So because both are having same orientation, so these two are not geometrical isomers. They are not geometrical isomers. Right?
okay,
Because when you say isomer, there has to be some differentiation between them,
difference,
right? There has to be some difference between the two entities. So here what we see is structure A and structure B, or orientation A and orientation B. But maybe the way we have written it is different. But in 3D, if you are going to give them some orientation, that this is one orientation one and this is orientation two, you will have to define that orientation, that two substituents are on the same side or opposite side. But here we see that that definition for both the structures are same, or both the representations are same. So that's why this very important condition for geometrical isomerism. This is very important. So just by seeing the molecules, you should be able to conclude whether there will be a geometrical isomer possible or not. So there has to be a restriction in the rotation of the bond. On top of that, both the substituents on the restricted atom must be different. So here you can see, if here you have A and B, and here you have A and B, or some other, say for example C and D, but this A and this, I mean this substituent and this substituent cannot be same. If they are same, as you can see here, there is a problem. You won't have a geometrical isomerism, right? And it says the geometrical isomerism is possible when these conditions are there. It doesn't say that there must be a geometrical isomerism when this condition is there. Let's see an example for that as well. Why it's right. It is a requirement. It is condition for GI. It is a required condition for GI. It doesn't guarantee geometrical isomerism. So what does that mean? So even that is very important to understand. See, C double bond C and this. So what we are seeing right now is cases of geometrical isomerism. So we are doing this so that during your exam, it is crystal clear in your mind where you will actually find geometrical isomerism. So this is a possible, again, we are saying possible. We are not saying must, right? So this is the first case. And let's say this case is for double bond. So first example is this, where you will see a double bond and possibility of a geometrical isomerism. Also, if there is a carbon double bond nitrogen, then this nitrogen can form only one bond, right? So how it becomes a case of geometrical isomerism? Because this nitrogen has a lone pair. So this lone pair can be oriented, I mean, if it is oriented here on the top or on bottom, right? So based on that, you will have two different geometrical isomerism. So there is a possibility here. There is a possibility here. Now, can you tell me whether there will be a possibility of geometrical isomerism in this case, in case of oxygen? In case of nitrogen, why it is possible? Due to this lone pair. So we will treat lone pair also as a substituent. Lone pair as a substituent. Now I'm asking whether geometrical isomerism, there is a possibility of geometrical isomerism here or not. Again, only possibility. So we don't know the substituents here. That's why we can't say anything about that. We cannot be sure about this. So that's why we say it is possible. It may be possible, right? Okay. So now in the third case, that is carbon double bond oxygen, is there a possibility of geometrical isomerism in third case?
No,
No. Reason?
because if we attach anything to carbon, then only that position would get reversed. We can't attach anything to oxygen unless it's a coordinate covalent bond.
Okay. Yeah, right. Or as I said here, this lone pair will be treated as a substituent. So here also you have lone pair as a substituent. But now what did you get? You have two substituents and both the substituents are same. So because they are same substituents. Lone pair means substituent. But because they are same substituent, that's why geometrical isomerism is not possible here. In nitrogen, there was only one substituent. Sorry, only one lone pair. So this lone pair and whatever will come here, that will not be a lone pair. So there is no problem due to nitrogen in the second molecule. Whatever problem may come, that will come due to the substituents of carbon. If the two substituents of carbon are same, then there won't be any isomerism. If the substituents at carbon are different, then there will be a geometrical isomerism. Simple. But in the second case, even if carbon has two different substituents, oxygen doesn't have two different substituents. They both are lone pairs. And that's why it is not possible. Whatever be the scenario, in this third case, the geometrical isomerism is not possible. So whenever there is an oxygen double bond or carbon oxygen double bond, oxygen is the culprit because oxygen has two lone pairs. And if the situation is like this, now you don't have any difference, or on both the sides, you don't have different substituents. So the culprit is what? Culprit is this oxygen. Due to oxygen, there won't be any. So this is to help you in exam to quickly find out whether geometrical isomerism is even possible or not. If it is not possible, then don't waste your time there in finding the geometrical isomers. Now let's move to the second case, that is case of triple bond. So what if there is a triple bond? It's very simple. If there is a carbon-carbon triple bond, then you have only one bond left for both the carbons. So there is no possibility, there is no question of different orientation, that is opposite or on the same side of the multiple bond. So in this case, you won't find any geometrical isomerism. Similarly, if there is a nitrogen-nitrogen triple bond, it is possible, right? So if there is a carbon-nitrogen triple bond. So if there is a carbon-nitrogen triple bond, even in that case, you can form only one bond here and nitrogen will have a lone pair here. So again, here, there is no question of geometrical isomerism in the triple bond. So that means when there is a triple bond, there is no geometrical isomerism. That means geometrical isomerism in your entire organic chemistry, which is in your syllabus, right, will be only these two. Only these two situations may have geometrical isomerism. First, in case of carbon-carbon double bond, both the substituents and both the carbons should be different. And in the second case, if you have different substituents here, you have geometrical isomerism. And same thing will be applicable for the ring structure as well. So in case of ring structures also, you can decide whether there will be a geometrical isomerism or not based on similar condition. So if it is like this, suppose here there are n number of carbons, right? It's not like there is only four carbon ring. It can have any number of carbons here. So these two carbons, right? These two carbons, you can choose any two carbons. So for example, A and B, these two are the restricted one. They cannot rotate. Now this A and B will have two more bonds if they are carbon, right? And if you have A here, this substituent should be different. If you have A here, so second substituent should be different, or it can be even entirely different from A and B, right? So it's very simple. If you have this, so whether you write A here or here, it doesn't matter. And that's why whenever you will find this, or you find it instead of double bond, if there is a ring, that means if this is the situation, right, there can be a ring here or there can be a double bond here. Let me show it by double bond only. So if this is the case, there won't be any geometrical isomerism. It is not possible to have geometrical isomers here, right? So now I'll give you different situations in which you will have to tell me whether there is a possibility of geometrical isomerism or not, right? So let me give you
I have a
these.
question.
Yes, go ahead.
So, could you explain the triple bond? When would they be geometrical isomer?
There won't be. It is not possible,
It's not possible, right? Okay.
right? Because the change in orientation is possible only if there is an alternative. Now, on each carbon in this case, or on each atom attached by a triple bond, there is only one bond possible now. So there is no scope of, so you are going to change the orientation. But where is the alternate place? There is no alternate place,
Yeah.
right? So there won't be any geometrical isomerism in case of triple bond. So geometrical isomerism is possible only if there is a carbon-carbon double bond or carbon-nitrogen double bond and other substituents. And those substituents should be different. Now let's see a few structures and you try to analyze that and tell me whether there is a geometrical isomerism possible or not, or whether it exists or not, because now I'm giving you the concrete structures. So there is no question in asking whether it is possible or not, just whether they exist or not. We should be very much clear about that.
Pairing failed. Please try again.
Okay, let me know once you are done.
I need to tell whether there is geometrical isomer.
Yes.
Okay. First one, it's not possible.
Okay, correct.
I don't think it's possible for the second one either.
Yes, because these two are same.
Yeah. Third one, I think it's possible.
Correct, because these are different. Even these two are different.
Mhm. Fourth one, no.
Fourth one, no, but why? There is a lone pair here, and this substituent is different. Similarly, there is a lone pair here, and this substituent is different. So I have not discussed it earlier, but it is possible.
Okay. Five, no.
Okay. What about 6?
6, no.
6, no. And the reason why 6 is not?
Yeah,
Because here
because,
there are 2 hydrogen,
yeah,
right? Okay. What about 7th? So here also there were 2 hydrogen, 2 hydrogen. I mean, these bonds were with the same atom. This hydrogen matched. So there is no isomerism. Okay, what about 7th?
possible.
It is possible because here there is a hydrogen, here hydrogen. So these two are different. Even these two are different. So geometrical isomerism is possible. Okay, so these are the conditions when geometrical isomerism is possible. Okay, now there are various other cases or reactions in which you will find geometrical isomerism. We will see that later. Okay, so now how to name them or how to identify two different orientations. How are you going to identify them? So we will have to have a nomenclature for them as well. So this is not, it's not the name which is going to be different. It is the configuration which is going to be different. And that's why this configuration, this is actually called configurational nomenclature. What does that mean? See here. The cases where isomerism is possible, right? This is the case where it is possible. So what will be the other structure? The other structure will be where this CH3 and CH3 will be on the opposite side. So here you can see they are on the same side. Here they are on the opposite side. So this is the possible orientation change. Now, if you try to give them their IUPAC name, so what will be the name? What will be the difference in name? So the name will be same actually, right? So this is first carbon, second carbon, third carbon, 4 carbon. So total 4 carbons. Here also 1, 2, 3, and 4. And the double bond is between 2 and 3. So it is the second position which will be taken as the position for the double bond. And that's why for both of them, the name will be same. That is but2-in. And if you recall in the structural isomers, that is chain or functional isomer or positional isomer or metamer or tautomer, the structure was different. And that's why in structure, it can be the chain length, which is different. It can be the branching, which can be different. It can be the position of a functional group which is different. It can be position of substituent which is different, or it can be entirely functional group which can be different. So there are these differences in the structure, and that's why the name will be different in case of structural isomers. But in this case, you can see here, only the orientation is different, structure is same, and that's why the name, the IUPAC name will be same. But there should be a method to differentiate these two orientation. So that's why we have this new, you can say, scheme of nomenclature that is called configurational nomenclature, obviously in case of geometrical isomers. So there are actually three systems which we are going to follow here, and we are going to follow all the three. It's not like only one of them is going to be used. That is cis and trans, and you have syn and anti or anti, and you have ENZ or ENZ. So these two. So one of the configuration will be called cis, another trans. One will be called syn, another anti. One will be called E, and the second one will be called Z, like that. So we will see one by one all of them. So first one, that is cis versus trans. When you see this, so this you will see in case of alkene, cycloalkene, or cycloalkane, right? So when you have a carbon-carbon double bond and there is A and B, it has to be different, so it is different. And then you have A on the same side of A. And then this can be anything. It can be your B as well as it can be anything else as well. Doesn't matter. So what we see here is if you have one pair of substituents on these two different atoms, the restricted atoms, right? If these two, I mean, the same substituents are on the same side of double bond, then this configuration is called cis. And if they are on the opposite side, that is, if you have C double bond C, here you have A, and on the second carbon, A is on the opposite side. This is called trans. So only thing is this has to be B, and this can be B as well as any other. So if you have one pair of substituent on the opposite side, that will be called a trans configuration. So you have a trans configuration and cis configuration. This is the difference. Is that clear?
Cis means it's on the same side and trans it's on opposite sides.
Correct.
Okay.
Okay. So if we go back to this, right, this third example, first part, say A, this structure is A and this structure is B. So A is cis or trans?
Cis.
And B is?
Trans.
Okay. In seventh, this is cis or trans?
Cis.
In sixth?
Six.
In sixth one?
Neither.
Correct. So it is not possible. There is no geometrical isomerism itself. Okay, so that is cis and trans. Actually, where you will find geometrical isomerism, or where you will find cis and trans and others, let's see that as well. So this was cis and trans, okay, and you know where will be cis and where will be trans. But what if the structure is like this? What if the structure involves this, right? So that means here, we know that there is a single bond here and a lone pair here. It is like this. right? What will be the other possibility in this case? That is when there is a lone pair. Other possibility of this is this C, double bond C, and sorry, not C, but nitrogen. And that nitrogen has a bond and a lone pair here, right? So first things is, this is the restricted atom. It has two substituents. They have to be different. So let's say they are different. It is like this, right? And this can be anything. It can be A, B, C. It can be anything. Now in this case, that is when you have this, right? In these two cases, what will be, can I use, say for example, if here it is A, and here also it is A, B, and A, then it's very simple that the second one is trans. You can say that second one is cis, and the first one is trans, right?
Right.
Okay. So in such cases, when you have situation like this, the thing is, right now what you are seeing here are the dummy, or you can say they are just generic compounds. You don't have a substitute there. So you will have to first understand when these compounds with carbon double bond nitrogen are formed and how it is formed. That information or that knowledge is important here. Without having that, we won't be able to we are this if you do something, if you find, or if you uh, come up with a configuration based on just this, it won't be same, right? It won't be correct, or you can say it won't be complete knowledge. So that's why what we are going to do here is we are going to have simple convention first. That is, before going to see how these carbon double bond nitrogen compounds are formed, before that, let's give a name for this. So what you are seeing here in the first case, right? It may not be possible that you have A here and here. If it is H and H, it is possible. Otherwise, it will be little difficult to give any name to this. So where you find this, let us see that one by one. So how it happens? Let's say there is R, C, H, double bond O, that is an aldehyde. So this is an aldehyde. Suppose this reacts with H, N, H, and some group here, right? This is a generic reaction which you will study later. But right now I'm just giving you the overview of such reactions. So in these reactions, what happens is you get R, C, H, double bond with nitrogen, and then that nitrogen is connected with the group. So this is the reaction, a very common or generic family of reaction, you can say. You just change the R and change the group, and you will have different compounds where there will be carbon double bond nitrogen. I mean, where you will find this scenario or this scenario, right? So the structure which you see here and the structure which you see here, these are same. There is a carbon nitrogen double bond. On carbon, there are two different identities or two different substituents. So that is settled. On nitrogen, there is a group, And obviously, there is a lone pair as well, which is not mentioned here. So you can actually think of this as, I mean, in order to understand the reaction, this should be this should be the picture. But if you want to understand the possibility of geometrical isomerism, then a better picture will be, or better representation will be this. So this will be the situation which you will find. Now this RNG can be same. RNH can be, RNH are anyways different. But instead of H, you can also expect another R. That is in case of when the first reactant is ketone. Right now, this reactant here is aldehyde. What if this is ketone? So in ketone, you will find geometrical isomerism only if R and R dash are different. So there are two possibilities. That is, you will get R. This is the first possibility, and second possibility where you will find this is this RR dash C double bond nitrogen and the group here and the lone pair over here. So it can have two possible. This second is in the case of when the initiator is a ketone instead of a aldehyde. So when this is a ketone, then ultimately you will get this. I'm not writing this reactant, but this is what you will get. That is when you have NH2G reacting with this, you will get this. So this first case and second case, these are the cases where you will get carbon double bond nitrogen. Now in this case, when will you say that there is what to say? How can I say? As you can see, R dash G in this case, in the second structure, R dash G and this lone pair. And in this case, you can see R, H, G and lone pair. So all the four are different. All the four substituents are different. It is the case of A, B, C, D. Right? So in this case, how are you going to name them? Obviously, what was that? Cis and trans won't work here because R is not opposite of R, and R are also not on the same side, right? Opposite to R in this case is G. They two are different. Opposite to R dash, it is lone pair. On the same side of R dash, there is G. On the same side of R, there is lone pair. So how can we decide whether it is cis or trans? So this actually leads to another configuration, which is syn and anti. Syn and anti. So syn and anti will be used when there is a nitrogen involved. So nitrogen involved like this, and even if there is so in first we'll finish this case itself. So if you have R, C, H, that is you got it from your aldehyde, right? Double bond N, then that N can have a lone pair here and a group here. Or when you have R, C, double bond N, now group here and lone pair here, and here H. So you have to observe H and G, that is hydrogen and the group. So there is no logic behind this. It's just a convention. It's just the way to form, because R can be anything, but H is fixed. right? So that's why we see, and lone pair is not visible to us in the structure. In the structure, we see the group. So when this hydrogen and the group are on the same side, then we say that this is syn configuration. And when this hydrogen and the group are on opposite side, we say that that is anti or anti configuration. So that is what syn and anti is. That is in case of aldehyde. What if you are getting it from ketone? So if you are getting it from ketone, that is your final compound, if that is coming from ketone, then how will that look like? That will be having R, C, double bond N. Here there will be R dash. This R and R dash have to be different. Otherwise there won't be any question of geometrical isomerism. So here you don't have anything. You have this lone pair here and the group here. So again, we have to name it. Still, we have to name it, right? So on what basis we are going to name it? Let's see that. So we will name it, if you see the previous case, right? G, that is the group connected to nitrogen, and H. So H was fixed because it was coming from aldehyde. So H was fixed. So that's why we took H and G. But and it was with respect to G. With respect to G, H is in syn position, and with respect to G here, H is in anti position. But here in the second case, now if you have to write, you don't have a fixed H on the carbon. You have R and R dash, and both are not fixed. It can be anything. It can be CS3, C2H5. It can be C4, H9, and C5, H11. It can be anything, right? So in this case, the convention which we use is we say that this structure with respect to G, R is at anti position and R dash is at syn position. So we name it like this. With respect to R dash, it is syn, and with respect to R, it is anti. So now you have fixed it. So this is one configuration. And other configuration will be what? Other configuration will be C, double bond N, G here. Sorry, if G is here and double bond is, sorry, lone pair is here, and if this is R dash and this is R. Now this one is what? This is with respect to R dash, it is anti position, and with respect to R, it is syn, not position, syn configuration. So we are saying with respect to G, everything is from the point of view of G, both in both the cases. Let me know if you understood this or not. Is it clear?
It's clear.
Okay. Are you finding it a bit confusing? If yes, you can let me know. And if you want to stop right now and do the rest later, I'm okay with that as well. So you
I have
can,
a question.
yes, go ahead.
How is sin different from cis?
Syn is different from cis. In cis, H and G were same.
Oh, right. I forgot. Yeah.
Okay, so that is the difference. In anti, H and G were same, but here they are different. Is it clear? Shall I move to the next?
Okay.
Okay, so this is when you have your compounds, when your compound or molecule has having carbon double bond nitrogen. There is another case of double bond, that is nitrogen double bond nitrogen. So when there is nitrogen, double bond nitrogen, what will you get? You will get a lone pair here and a group, which can be A or anything. And there can be A here, and there will be a lone pair over here. So even if it is different, here I have a lone pair opposite of each other. And other possibility is nitrogen, double bond nitrogen, lone pair on this nitrogen also, lone pair here, and then here A, and here it can be A or B, anything. Now what I see here is I can make the decision based on lone pair itself. But it was not possible earlier when there was only one lone pair only on nitrogen. If you see the above case, right, on carbon there was no lone pair, so lone pair and lone pair were not matching. But here I can take the decision based on only lone pairs. So if lone pair here and lone pair here, they are opposite, this will be anti. So I don't care what is here and here. That is insignificant. Just based on lone pair, I can give them two different configuration. So this is similar to cis and trans. But in cis and trans, there was no lone pair. In cis and trans, they were actual substituents. Here, they are lone pairs. It is actually absence of substituents in those places. Is this scheme or is this scheme of orientation nomenclature clear?
Yeah.
Okay, so there are two places where you will be finding syn and anti configuration. That is carbon double bond nitrogen or nitrogen double bond nitrogen. There is one case where you will find cis and trans. That is when there is a carbon double bond carbon or there is a ring. Right? So cis and trans will be only in those cases. As soon as nitrogen comes into picture, there is a lone pair and it changes to syn and anti. Okay, so we will see examples of it later. Right now, let's move to the next possibility. That is, what if you have carbon-carbon double bond and you have AB here and C and D here. Now, how can you decide? So there is no lone pair. So that means syn and anti is gone. And all the substituents are different. So there is no duplicate substituents which are on the same side or on the opposite side. So I cannot even use cis and trans. Do you agree?
They're all different though, right?
Yeah, all are different.
Yeah.
So can I use cis and trans?
No.
Can I use syn and anti?
Yeah.
No. In syn and anti, there has to be a lone pair.
Okay.
If you go back and see the syn and anti, there was a nitrogen molecule, nitrogen atom, and on nitrogen atom there was a lone pair. So now, and everything was either based on that lone pair or from the point of view of that group which is attached to the nitrogen atom. But here there is no nitrogen atom, so I can neither use cis and trans and nor syn and anti. Clear? So that means there's a need for a new system, right? Because if C and D change their position, if C and D exchange their position, that will be a different configuration. So there should be two different names or two different adjectives added to these two different configurations. right? So how to see that, or how to find, or how to solve that problem, we will see that next. So let me know if you want to continue. Okay. So so what if this situation, how are we going to solve it? So again, there's no rule and all here. uh, I mean, there is no law here. uh, Whoever has seen this situation, he just gave a solution for this. So the nomenclature which we are going to use here is called E or Z nomenclature. So just like syn and anti, cis and trans, there is E and Z. So it will be used when there is C double bond C or cycloalkane and all the four are different. When all four substituents were in carbon double bond carbon or a cyclic compound are different. So only in that situation you will be using it, right? They actually use CIP rule. What is CIP rule? So these are three scientists, Kohn, Ingold, and Prelog. So these are three scientists who formed this rule. So they use this. This is actually the convention in which the priority of substituents come into picture, and we will see that as well. What exactly is priority of substituents? So the four substituents will be having their own priority, right? And then comes the main point. That is, if two high priority, so for the timing, just assume priority is something which is given to all these substituents. So when two high priority substituents attached on the same side of restricted atom, right? Then it is called Z, else it will be called E. This is what E and Z
Trying failed. Please try again.
scheme is, right? So we will see, I'll explain it with an example. The first thing is, how are you going to define what is the priority? So that is very important, but we'll come to this later. First, understand what does this statement mean, right? That is two high priority substituents attached on same side of restricted atom. Then you give it Z configuration, otherwise you give it E configuration. What does that mean? So let's say you have a molecule in which it is like this. So we know that when E and Z will come into picture, when you have when you have all the four substituents different. So let's say this is one such configuration, right? And
Connected.
the substituents A and B are connected to C. And let's say that A's priority is greater than B. Priority is something, let's say A's priority is greater than B. And in the second one, let's say C's priority is greater than D. So now if you see, if you have to encircle the high priority one, so it is the A and C, and they are on the same side of double bond, or they are on the same side of the restricted atoms. And that's why this will be called Z configuration. Right? But okay, And but if let's say you have this C double bond C, here you have A, B, and here you have, say, PC. And the same thing, that is, A's priority is greater than B and C's priority is greater than D. So C is higher priority and here A is higher priority. Now the higher priority elements are, or substituents are, on the opposite side. So because they are on the opposite side, so this configuration will be called E configuration. Is it clear?
Yeah.
So that is what
It's
is E and Z configuration. Now the only thing left here is how to decide the priority. What should be the criteria of attaching priority to a particular substituent? So this priority is relative. So between A and B, it can be A. And on the other side, if you have A and C, it is possible that C may have higher priority than A. So it is possible. So this priority is relative. But how to find that? So it is not based on size and anything else. This priority is actually based on the atomic number. But the thing is, you don't have always one atom attached to the carbon. It can be multiple atoms, or I mean it can be a group of atoms that is nothing but a substituent other than just a simple atom. So in that case, how are you going to find the priority? So the criteria remains same, that is atomic number. Okay, so we'll start with, so this is what CIP is, CIP rule, that is Kohn, Ingold, and Prelog. And this CIP rule is very important because we will be using it again in a different isomerism nomenclature. So try to be careful here when I'm explaining you this, how to give priority to the substituent using the CIP rule. So first thing is that priority is based on, or it is decided by, the atomic number. What does that mean? So let's see an example first. Let's
mass
see.
number, right?
Uh,
Mass number,
Not mass number,
quota.
atomic number. See, mass number, there is a possibility of having same mass number, but atomic number will be always different. So that's why we are using the atomic number instead of mass number. So now if you see here, fluorine, chlorine, bromine, iodine, it is like this. So out of fluorine and chlorine, chlorine will be the higher priority. Out of bromine and iodine, it will be iodine which will have higher priority. So now tell me, what is this configuration, E or Z?
Chlorine, chlorine and iodine would be of higher priority.
Yes,
This configuration is Z.
this configuration is Z configuration, correct? Okay, now this is in case when you have simple atoms, single atoms connected to carbon. Obviously, that is very a small fraction of so many compounds which you will see in organic chemistry. What if you have compound like this? What do you think? How are you going to decide the priority first?
Atomic number, right?
Yes. So pay attention here. Atomic number of the atom directly connected to carbon. So which is the atom directly connected to carbon? That is what you have to decide first. That is what you
Okay.
decide first. Don't go on the size of substituent or
Is
on the
this E
complexity.
structure then?
What?
Is this
So
E?
first you will have to see that which one has the higher priority. So this nitrogen is
Bromine and nitrogen.
bromine and nitrogen. And that's why this will be E configuration. Clear? So that is E configuration. Okay, now in the same, what if the compound is this CH2, CH3, CH3, and here you have OH, and here you have OCH3. What if this is the molecule? So the problem here is what? Both are carbon. Right? So what you do in this case, these two hydrogens are actually here. The next atom attached to carbon other than hydrogen. So if it is not clear by the first directly attached, move to the next. If no difference, then there won't be any geometrical isomerism. So here we see that here I cannot make any decision because both are carbon. So I move to the next atom. So the next atom is what? Carbon. So this is carbon. And here what is next atom? Next atom here is hydrogen. So obviously, I hope you understood, right? There are two hydrogen here. And then the carbon is attached to, it is like this, carbon, hydrogen, hydrogen, carbon, hydrogen, hydrogen, hydrogen. This is what it is. And what is this? Carbon, hydrogen, hydrogen, hydrogen. So this is the first atom which is connected. This is the first atom which is connected to carbon. So both are same. What will you do? Move to next. These two are same. Move to next. Move to next. This and this. So this carbon has the higher priority. So this is higher priority. Compare this
Okay.
again. Oxygen and oxygen are same. So what are you going to do next? Next, see here, hydrogen, here, carbon. So this is crystal clear. This is the higher priority. So higher priority and higher priority are on the opposite side. So the configuration is E configuration. Is it clear?
Yeah.
Okay, so that was about the E and Z configuration and the CIP rule, which is very important rule, which helps you in giving the priority. So in priority, what you have to do is you have to concentrate only on the atomic number of the directly connected atom to the carbon. That is the carbon-carbon double bond. If they are same, then you move to the next, as we have seen in this example. So we move to the next atom to break the tie. When you can see on the left hand side, you had oxygen and oxygen both same, and on the right hand side as well, you have carbon and carbon same. So the decision will be taken by the next carbon atom. And if there is no difference, then there won't be any geometrical isomerism. Although it is a candidate of geometrical isomerism, but if there is no difference in the substituents, then we know that there is no geometrical isomerism.
When there's no difference in
substituents. If both the substituents
Oh.
on carbon is same, that means there is no geometrical isomerism itself.
Yeah.
Right? So I hope all the three systems, that is first cis versus trans, this comes into picture when there is a carbon-carbon double bond and you have something like this, AB or BA. So here you will have cis and trans. Then we have syn and anti, that comes into picture when there is a carbon double bond nitrogen or nitrogen double bond nitrogen. And then there is last one, that is EZ, when all the substituents, the four substituents are different, then we will be using ENZ system. So this is the, you can say, the summary of this geometrical isomerism. Okay, so that's all for today. We'll continue in the next class.
Okay. Thank you, sir.